The first bit of Deform news is we're going to do the first quiz on Friday. So the first lecture quiz is this Friday. Remember that these are always cumulative, so to get ready for these, you need to go back to the start of your notes, read through the notes. I think doing class outlines is helpful overall, and I think it's helpful for these, just to get in your head where the different parts of the class fit together, what were the main things that I was trying to point out, you know, as you go to the different sections. I think it can help you sort of clarify that stuff to yourself. So, you know, at a minimum, just skim through your notes and try to remember what seemed like the big ideas as well as you can. But if you skim through it multiple times, you know, it wouldn't hurt, I don't think, to write an outline or a summary and make mental notes of like what the key points are and that kind of thing. Okay, anybody have any homework questions? Okay. The next overall topic is stresses in beams. We're going to start with sort of a review of internal loads in beams. And so remember that, you know, like for example, you have a beam like this, and you have external loads applied to it in some way. And at every location along the beam, we basically find the loads applied to one side of the beam by the other side. And you can do this one by one, you know, you can choose a point and calculate the loads applied by the adjacent material. And that's easier to do, but the problem is then you only have that information at one point. What we prefer to do is come up with those internal loads as a function as you move along the beam. It's a little more tedious, but then you only have to do it once and it represents the whole beam, instead of sort of the way a computer would approach this would be to calculate the internal loads at a bunch of finite points pretty close together and just try to draw conclusions based on that. Okay, so, well, what are we going to, so what are stresses in beams compared to internal loads? How do the stresses compare to these internal loads? Well, let's think about what we learn from the internal loads. So internal loads, let's not use differentiate. Let's say make a distinction between different locations along the beam's long axis but here's what they don't do. They don't take into account changes in the geometry of the beam. In other words, if you had a beam that was a millimeter thick, well, like think of a set of internal loads. So 400 newtons for tension, 650 newtons for shear force, 100 Newton meter bending moment. Is that a lot? Are we worried about this thing breaking? Who knows? We don't know anything about the shape of the beam. If it's a millimeter thick, then yeah, it's going to break it. If it's half a meter thick, then it won't even notice that. And so calculating stresses instead of just internal loads is going to give us that ability. And the second thing that internal loads don't take into account is they don't distinguish between different points on the same cross section of the beam. Okay, so if this is a beam, and at that cut there, we know that there's some internal loads. Well, so we can calculate the internal loads at that cut, but we can't say anything about, well, what's the difference between the stresses at those 2 points, or at the middle versus the end here. Are you with me on that? So calculating the stresses is going to give us both of those two things. Calculating will allow both of these. Well, to calculate the stresses in a beam, you first have to calculate the internal loads, and then the stresses are all going to be calculated from the internal loads. So for beams, we'll first calculate internal loads. Then we'll use those to calculate the stresses. One thing that's different now that we didn't talk about in statics is torque. That's a pair of couples in opposite directions along the long axis of the beam. We could have done it in statics, but we didn't because people normally don't. But now, one difference, this is the only difference from internal loads in statics. Is now will include internal torques. We had internal bending moments, but now we're going to have internal torques also. And for physicists, torques and moments are totally interchangeable words. Engineers don't tend to do that because the reason is in engineering, a torque is this specific combination of equal and opposite couples that provides like a twisting stress and strain to a material. Okay, so that's why I always use moments and not torques. Okay. So I'm going to start with I'm going to just start with an example and just build on that. So let's say we have a cantilever beam. So it's supported at one end. And we're ignoring the weight of the beam. And the only loads are this 1,000 Newton force at the end that makes an angle of 45 degrees with the horizontal. And then a 500 Newton meter couple about the x-axis. That's what we haven't dealt with before. Let's say that the whole thing has a length of 1 meter. And we want to calculate the internal loads at the midpoint. In this problem, actually, it would be a little easier to do this calculation from the right side, but I'm not going to do that. I think let's just always get in the habit of working from the left side. And so the first thing I'm going to do is calculate the external loads that are applied by the wall. So let's think of what that looks like. You have the 1,000 Newton force here. You have the 500 Newton meter couple here. And this is a fixed joint. So we know we have an unknown force vector here counteracting any forces along the beam. So I'll call this R. And we also have a full vector of couples available from that fixed joint, but we're never going to be dealing with calculations where, like you can imagine applying a force this way would require the wall to apply a couple about the y-axis. We're not going to ever deal with those. Like if you have something like that, just flip the problem in your mind so that it's in the plane that we're used to dealing with. Okay. So what moments are applied? There's still a moment like this. I'm going to call that M, R. I didn't give you a coordinate system, did I? So let's use a coordinate system with X along the beam, Y-axis up. That means Z is coming out towards us. Okay, so this moment that I drew here, what axis is that around?
Z.
Z, yep. And then we also need a couple to counteract this 500 Newton meter couple. That's what's new. You haven't seen that before. And I'm just going to represent that like this with the double arrows to say this is a couple about the x-axis, a couple in this direction. And that's going to be MRX. So remember that the direction of a couple vector is always the direction your thumb is pointing in the right-hand rule. Okay, so what this is saying is this component of the couple is applying a twisting, load this way on that beam. Okay. And now we're going to calculate those. I'll do Newton's second law first. So we have Rx, Ry, plus this force is negative 707.1, negative 707.1. The couples don't produce any force because the nature of couples is they cancel each other out as the forces cancel each other out, remember? And so this is all we need for Newton's second law. And so that reaction load is positive 707.1, positive 707.1. And now we'll do the moment equation, but I'm just going to do it component by component. I mean, you could do it as a vector, but we're not, the y component is always going to be 0 equals 0 anyways. So I'm just going to do it as, so we'll do rotational Newton's second law about the x-axis. And these are all just couples. So what we have here is MRX plus 500 is equal to 0. So MRX is equal to negative 500. So that says that this couple is actually 500 Newton meters going that way, which obviously you can just tell from just eyeballing it if you have to cancel that force on the right end. And now we'll do the Z. So we have MRZ. And the only thing that produces a moment about the z-axis is this 1,000 Newton force. Okay. You could write out a table, do this as a rigid body problem. But also you can just, the x component of this force isn't going to produce a moment. So you can just take the y component of this force and think of it as straight down at that point. So that's going to be a force of 707.1 with a moment arm of 1, making it rotate this way. So this is going to be, that's going to cause a downward force of 707.1 is going to, okay, one thing I skipped. What are we choosing as the about point here for the, yeah, I just always use the left endpoint for these. So if we didn't use the left endpoint, you'd have to account for the y-axis of that R reaction force. But the reason we don't is because I'm assuming, yeah, I'm choosing my about point to be where R acts. So, okay, about this point, that downward force of 707 would produce a clockwise rotation if nothing was counteracting it. So that's going to be a negative moment with a moment arm of 1 and a force of 707.1. Are you with me on that? That's equal to 0. So MRZ is equal to positive 707.1 Newton meters. Now we have our external loads. Now I'm going to do my cut. So for my cut, I'm going to include all the stuff to the left of the cut. And I'm going to ignore all the stuff to the right of the cut. Okay, which means I'm ignoring this force. I'm ignoring this couple. But what I'm not ignoring is all the stuff in black. So we had a force of 707.1, 707.1. And a couple about the z-axis of 707.1 Newton meters. Just, that's a reminder, that's a couple. And then we have a couple about the x-axis pointing to the left of 500. And since we're not including any of the stuff in light blue, the only other loads we have are the internal loads on the right side of this cut. So remember, that's a tension T, a shear force V, a bending moment M. That's really a Z component of a couple. And then another couple that I'm going to call the torque, fancy T. Be sure to make it fancy or you'll mix it up with tension. Okay? And now we can use Newton's second law. One thing I want to point out, I pointed this out in statics, but this is the craziest sign convention anyone has ever come up with. So I want you to just remember that this is just some insane person's idea of how to represent. All it's representing is a force vector and a couple vector. It's just choosing these crazy positive directions. Now, the reason that we didn't just use straight force vectors, so T and V make a force vector in the plane, right? They have a funny orientation. The reason we just didn't keep the same sign convention is if we did just call this, say we just call this a reaction, we call it an R vector or something, then we calculate one thing where we isolated this side, and we calculate the opposite if we isolated this side. And it's confusing if you have it that way. What we want is a single set of internal loads that's going to give us the same answer whether we isolate this or isolate this. We want to have just a set of internal loads that tell us what this is, no matter how you calculate it. So we had to choose a new sign convention. And we left that up to the craziest person we know. And that person said, let's make everything be like in the vector directions except the y component of the force. And we'll give each one individual names, okay? And we're just like, bravo, like that is as crazy as we hoped it was good.
Nobel Prize.
What?
I said Nobel Prize.
Yeah, exactly.
It was you that did it, wasn't it?
No, I would not have done it. But just remember that these two are a force in the plane. These two are two components of a couple vector. It's really a simple idea, but you have to use this crazy sign convention. Okay, so Newton's second law says 707.1, 707.1, plus T0 plus 0 negative V is equal to zeros. And remember, you can always think of those arrows as unit vectors, and you're multiplying that variable to the unit vector. So that's where these vectors come from. The arrow associated with that tension is in the positive x direction, so its unit vector is 1, 0. Multiply that by t, and you get T0. The shear force, that unit vector is 0, negative 1. Multiply that by v, and you get 0, negative v. Okay, so the x equation says T is equal to negative 707.1 newtons. So at this point, is it in tension or compression? Compression, yep. Positive is tension, negative is compression. And then V is equal to positive 707.1. So those are our two internal forces. And now we'll go to the moment equation about the x-axis. These moments are really easy because all you have is couples. You're never worrying about moment arms or anything like that. We have negative 500 plus fancy t is equal to 0. So fancy T is equal to 500 Newton meters. And then we'll do the Z equation. Again, our about point is going to be here at the left. Just always do that the same. It'll keep you from making dumb mistakes. And so the force vector at the left end is at the about point, so that's not going to produce a moment. We have a positive couple of 707.1 acting at the left end, so that's this. Then we have the bending moment at the right end, the M. And then the last thing we have is the moment produced by V around that about point. The length of this thing, since we're at the midpoint, is 0.5. So, you can think of this as plus or minus moment arm of 0.5 times V. Now think about if that force was alone, would it make this body rotate clockwise or counterclockwise around that about point? Think about it and then say it to me verbally.
Clockwise.
Right. So this is going to be the negative. That's everything that produces moments about the z-axis. And so we get m is equal to 0.5 times v, which we already calculated. Minus 707.1. And so the bending moment is equal to negative 3353.5. Is that right? Okay. And that's Newton meters. Okay, and for our purposes in this class, this is just the starting point to being able to calculate the stresses, and that's what we're going to get to pretty soon. But first you have to calculate the internal loads at a point, and then you can use those to calculate the stresses. Okay, well, we don't usually do it point by point like this. So let's do it now where instead of choosing a specific point, we represent the cut point by the variable x, and we just calculate these internal loads as a function of x. Okay. So now instead of choosing a specific, let's say x value, we want to calculate the internal loads as a function of x. Okay, so we're going to do a cut that represents that this is going to be valid for all the x's between the left end and the right end. So this x value could be anything from 0 to 1. And we're going to do basically exactly what we just did, except this time we don't know what this distance is. We're just calling it x. And the loads are a force of 707.1, 707.1 at the left end point. A moment about the z-axis of positive 707.1 Newton meters. And then an x component of a couple with a magnitude of 500. And then at the other end, we have the internal loads, T, V, M, fancy T. Newton's second law says 707.1, 707.1 plus T, T0 and 0 negative V. You can lump that into a single vector. And you get that t, no matter what that x distance is equal to negative 707.1. V, no matter what that x distance is positive 707.1. Now the x couples, we still have our about point here on the left. So we have negative 500 plus fancy t is equal to 0. So no matter what the x is, that internal torque is 500. And then the moments about z, we have the couple on the left. We have the bending moment on the right. And then we have a clockwise moment, so negative, with a moment arm of x and a force magnitude of v. So we have m is equal to positive vx minus 707.1 and so m is equal to, we've already calculated v, so substitute that in. And you get 707.1x minus 707.1. How many cuts do you need? So identify all the points where external point loads are applied. Distributed load functions change. And beam endpoints. Don't double count these points. So this is like, they can have any of these, okay? If there are n of those, you're going to need n minus 1 cuts. Okay, let's do sort of a quick one so I can fit it in before class ends. So let's say this distance is 1 meter, and this distance is 1 meter. And let's say this is 1,000 Newton force, and we'll have an applied couple in the x direction of 200 Newton meters. And we want to calculate the internal loads as a function of x. Well, the first thing we have to do is calculate the external loads. So I'll isolate the whole thing. That's 1,000 newtons, 200 Newton meters there. The pin joint at the right end applies an unknown force vector. I'll call that RB. And then the roller applies a force toward the body, perpendicular to the surface. I'll call that RA. So Newton's second law says 0, negative 1,000 plus 0 RA plus RBX RBY is equal to zeros. I guess we can't calculate it yet. So go to the moment equation. I'm going to put the about point here. So we have the moment from RA. It has a moment arm of 1, a force of magnitude of RA. And would that make it rotate clockwise or counterclockwise around that about point? Counter, yep, so that's positive. And then we have plus or minus. Only the y component of this is going to produce a moment. The x component, its line of action goes right through that point. So that has a moment arm of 2, a force magnitude of RB. And is that clockwise or counterclockwise? The RBY would be counterclockwise, so it's another positive. And this is equal to 0. So we have RA is equal to negative 2 RB This is RBY, by the way. Okay, and now we can solve this. Let's see. From the y equation in Newton's second law, we have negative 2 RBY plus RBY is equal to 1,000. So RBY is equal to negative 1,000. RBX up here you can see is equal to 0. And RA is equal to 2,000. Okay? Okay, so how many cuts are we going to have? So yeah, we have these key points are the two endpoints, where the roller is, and that's it. So n equals 3, and that says we're going to do 2 cuts.
So did we do the rotational equation for the x?
Nope. Okay, so this would be, so this is the z moment equation. So now we have to do it for x. Totally blanked on that, because in statics we never do that, you know. So
we have that 200.
yeah, so we have negative 200. And then this, if you think about what would counteract this rotation, it's going to be that pin joint at the end. So I'm going to call this torque R, the reaction torque. So negative 200 plus TR is equal to 0. And so TR is equal to positive 200 Newton meters. Okay, so where did that thing go? All right, so n is equal to 3. So we're going to do 2 cuts. The first one is going to be somewhere before you get to that second point. So that's cut 1. And the second one is going to be somewhere after you get to that second point. So that's cut 2. And those dots are supposed to represent which of those external loads appear in what cut. Okay.
Do you want the distance where that middle point is? Should be 1 meter. So like x from 0 to 1.
Yeah. Yep. Right. So this is, so cut 1 is going to be x values from 0 to 1. And cut 2 is going to be x values from 1 to 2. Okay, any questions about that? So I guess we're not going to finish this today. Let's just stop there. I'll finish this next time. I'll give you some simple internal loads problems to do. If you have trouble with any of them, bring them to class and we'll do them in class. And we'll just get this stuff straight again. Okay. So yeah, remember a quiz on Friday.
Yeah.